universe stretches before us in all its magnificent glory, a tapestry of countless stars, swirling galaxies, and cosmic phenomena that have captivated humanity for millennia. When we gaze up at the night sky, we see more than just points of light scattered across the darkness. We see the grand theatre of existence itself, a cosmic stage where the fundamental forces of nature play out their eternal dance. For centuries, our greatest minds have sought to unlock the secrets of this vast expanse. From ancient astronomers who first mapped the constellations to modern physicists probing the deepest mysteries of quantum mechanics, we have always yearned to understand the true nature of reality. What drives the motion of planets? What ignites the fires of distant suns? What invisible forces shape the very fabric of space and time? But what if we have been thinking about the universe in the wrong way? What if the cosmos is not merely a collection of matter and energy governed by physical laws, but something far more profound and revolutionary? What if the universe itself is performing calculations, processing information at the most fundamental level of existence? Consider for a moment the intricate patterns we observe throughout nature. The spiral arms of galaxies follow mathematical principles with stunning precision. The behavior of subatomic particles obeys quantum rules that seem almost algorithmic in their complexity. The very structure of space and time appears to be quantized, broken down into discrete units like the pixels on a cosmic computer screen. This is not mere speculation or science fiction fantasy. Leading physicists and cosmologists are seriously exploring the possibility that our universe functions as a giant quantum computer, processing information and executing calculations on a scale that dwarfs anything we could ever imagine. In this computational cosmos, every particle interaction, every quantum measurement, every moment of cosmic evolution could be part of an immense calculation unfolding across billions of years. The implications of such a reality are staggering. If the universe is indeed a quantum computer, then everything we know about existence, consciousness, and our place in the cosmos must be reconsidered. The stars above us might be processing nodes in a vast computational network. The empty space between galaxies could be filled with invisible calculations. Even our own thoughts and experiences might be part of this cosmic computation. Tonight, we embark on a journey through this extraordinary hypothesis. We will explore the cutting edge of quantum mechanics, delve into the mathematics of computation, and examine the profound philosophical questions that arise when we consider the universe as a giant thinking machine. We will visit the laboratories where quantum computers are being built and discover how these remarkable devices might give us clues about the computational nature of reality itself. This is not just a story about advanced physics or computer science. It is a story about the deepest questions of existence. Are we living inside a cosmic simulation? Is consciousness itself a form of computation? Does the universe have a purpose, an ultimate calculation it is trying to complete? These are the mysteries we will explore as we venture into the realm where science meets philosophy, where the quantum world reveals its secrets, and where the universe itself might be the ultimate computer. So settle in as we begin this extraordinary exploration. Let your mind wander through the cosmic vastness and prepare to see the universe in a completely new light. The journey we are about to take will challenge everything you thought you knew about reality, and perhaps reveal that the cosmos itself is the most sophisticated computer ever conceived. To understand how the universe might function as a quantum computer, we must first explore what computation truly means. The story of computation begins not with silicon chips and electronic circuits, but with the fundamental human desire to solve problems and process information. Picture the ancient mathematicians of Babylon, using clay tablets to perform calculations that would help them predict the movements of celestial bodies. Or imagine the brilliant minds of ancient Greece developing geometric principles that still guide our understanding of space and form. These early thinkers were already engaging in computation, using systematic methods to transform information and arrive at new insights. The first mechanical computers were marvels of engineering ingenuity. In the 17th century, Blaise Pascal created a mechanical calculator that could add and subtract numbers using an intricate system of gears and wheels. Later, Charles Babbage designed his analytical engine, a mechanical computer that could theoretically perform any mathematical operation. Though never completed in his lifetime, Babbage's vision laid the groundwork for the digital revolution that would transform our world. But what exactly is a computer? At its most basic level, a computer is any system that can take information as input, process that information according to a set of rules or instructions, and produce a meaningful output. The human brain is a biological computer, processing sensory information and generating thoughts and actions. An abacus is a simple mechanical computer, manipulating beads to perform arithmetic. Even a simple light switch is a form of computer, processing the input of your finger press and producing the output of illumination. The computers we use today operate on the principle of binary computation. Every piece of information, whether it is a photograph, a piece of music, or a complex mathematical equation, is ultimately represented as a series of ones and zeros. These binary digits, or bits, are the fundamental units of digital information. A computer processes these bits through logical operations, following algorithms that specify exactly how the information should be manipulated. Think of an algorithm as a recipe for solving a problem. Just as a cooking recipe tells you step by step how to combine ingredients to create a dish, an algorithm tells a computer step by step how to process information to solve a computational problem. The algorithm for adding two numbers might involve breaking them down into their component bits, performing addition operations on each bit position, and handling any carries that result from the arithmetic. The power of digital computers lies in their ability to execute these algorithms with incredible speed and precision. Modern processors can perform billions of operations per second, following algorithmic instructions with perfect accuracy. This computational power has enabled us to simulate weather patterns, design complex structures, decode the human genome, and even explore the cosmos through sophisticated computer models. But there are limits to what classical computers can achieve. Some problems are so complex that even the most powerful supercomputers would require millions of years to solve them. These problems involve so many variables and possible combinations that classical computation becomes impractical. This is where quantum computation enters the picture. Quantum computers represent a completely different approach to information processing. Instead of using classical bits that can only be in a state of 0 or 1, quantum computers use quantum bits, or qubits, that can exist in a superposition of both states simultaneously. This quantum property allows a quantum computer to explore multiple solutions to a problem at the same time, potentially solving certain types of problems exponentially faster than any classical computer. The mathematics behind quantum computation is mind-bending. A single qubit can represent both 0 and 1 simultaneously, but when you measure it, you will observe only one of these states. 2 qubits can represent 4 different combinations of states simultaneously. 3 qubits can represent 8 combinations, and so on. With just 300 qubits, a quantum computer could theoretically represent more states than there are atoms in the observable universe. This computational power emerges from the strange rules of quantum mechanics. In the quantum world, particles can exist in multiple states at once, can be instantaneously connected across vast distances, and can influence each other in ways that seem to defy our everyday understanding of reality. These quantum properties, once seen as mere curiosities of physics, are now being harnessed to create a new generation of computational devices. Quantum computers are already being built and tested in laboratories around the world. They are being used to simulate molecular interactions, optimize complex logistical problems, and explore the fundamental properties of matter and energy. As these machines become more powerful and more practical, they may revolutionize fields ranging from medicine to materials science to artificial intelligence. But here is where our story takes a fascinating turn. What if the principles that make quantum computers so powerful are not just useful tools for human technology, but the very principles that govern the operation of the universe itself? What if the cosmos is not just a collection of matter and energy, but a vast quantum computer, processing information and executing calculations on a scale that encompasses all of reality? The idea is not as far-fetched as it might initially seem. The laws of physics themselves can be viewed as algorithms, systematic rules that govern how matter and energy behave. Every interaction between particles, every quantum measurement, every moment of cosmic evolution could be seen as a step in an immense computational process. The universe might be computing its own future, processing the information contained in its current state to determine what will happen next. This perspective transforms our understanding of existence itself. If the universe is a quantum computer, then everything we observe, from the smallest subatomic particles to the largest galactic structures, might be part of an ongoing calculation. The stars might be processing nodes in a cosmic network. The empty space between galaxies might be filled with quantum information. Even our own consciousness might emerge from the computational processes of this universal quantum computer. The evolution of computation has been driven by our relentless pursuit of efficiency and capability. Early computers filled entire rooms and consumed enormous amounts of electricity just to perform calculations that a modern smartphone can complete in microseconds. The ENIAC, one of the first electronic computers, weighed 30 tons and required 18,000 vacuum tubes to operate. Today, we carry devices in our pockets that contain billions of transistors, each one smaller than a virus, working together to process information at speeds that would have seemed magical to the pioneers of computing. This miniaturization has followed a predictable pattern known as Moore's Law, which observed that the number of transistors on a computer chip doubles approximately every 2 years. For decades, this exponential growth has driven the advancement of technology, enabling everything from personal computers to the internet to artificial intelligence. But as transistors approach the size of individual atoms, we are reaching the physical limits of classical computation. At the atomic scale, the familiar rules of classical physics give way to the strange and counterintuitive world of quantum mechanics. Electrons can tunnel through barriers they should not be able to cross. Particles can be in multiple places at once. Information can be transmitted instantaneously across vast distances. These quantum effects, which once seemed like obstacles to further miniaturization, are now being harnessed to create entirely new forms of computation. The concept of quantum computation was first proposed by physicist Richard Feynman in 1981. Feynman realized that classical computers would never be able to efficiently simulate quantum systems because they would need to track an exponentially large number of possible states. He suggested that quantum computers, which could naturally handle quantum superposition and entanglement, might be the key to unlocking the secrets of the quantum world. The development of quantum algorithms has revealed the extraordinary potential of quantum computation. Shor's algorithm, developed by mathematician Peter Shor in 1994, can factor large numbers exponentially faster than any known classical algorithm. This capability threatens the security of current encryption systems, which rely on the difficulty of factoring large numbers. Grover's algorithm can search unsorted databases quadratically faster than classical methods, potentially revolutionizing data processing and artificial intelligence. But building practical quantum computers has proven to be one of the greatest engineering challenges of our time. Quantum states are incredibly fragile and can be destroyed by the slightest environmental interference. The qubits in a quantum computer must be isolated from heat, vibration, and electromagnetic radiation. They must be cooled to temperatures colder than outer space, just a few thousandths of a degree above absolute zero. Even under these extreme conditions, quantum states can only be maintained for fractions of a second before they decohere and lose their quantum properties. Despite these challenges, remarkable progress has been made. Companies like IBM, Google, and dozens of startups are building quantum computers with increasing numbers of qubits and improving reliability. In 2019, Google claimed to have achieved quantum supremacy, demonstrating that their quantum computer could solve a specific problem faster than the world's most powerful classical supercomputers. While the practical applications of current quantum computers remain limited, they represent the first steps toward a new era of computation. The implications of quantum computation extend far beyond faster calculations. Quantum computers could revolutionize drug discovery by simulating molecular interactions with unprecedented accuracy. They could optimize complex logistical problems, from traffic management to supply chain coordination. They could break current encryption methods while simultaneously enabling new forms of quantum cryptography that would be theoretically unbreakable. Perhaps most intriguingly, quantum computers might help us understand the nature of reality itself. If the universe operates according to quantum mechanical principles, then quantum computers could be the ideal tools for simulating and understanding cosmic phenomena. They could help us model the behavior of black holes, understand the nature of dark matter and dark energy, and even explore the possibility that space and time themselves emerge from more fundamental quantum information. This brings us to the heart of our investigation. The same principles that make quantum computers so powerful, superposition, entanglement, and quantum interference, are the fundamental principles that govern the behavior of the universe at its most basic level. Every particle in the cosmos obeys quantum mechanical laws. Every interaction between particles involves quantum processes. Every measurement or observation causes quantum systems to evolve and change. What if these quantum processes are not just the underlying mechanics of reality, but the computational processes of a cosmic computer? What if the universe is not just made of matter and energy, but of information and computation? What if every quantum interaction is a computational step in an unimaginably vast and complex calculation? The idea gains credibility when we consider that information appears to be a fundamental feature of reality. The physicist John Wheeler proposed that information, not matter or energy, might be the most basic constituent of the universe. His famous phrase, "it from bit," suggested that every physical quantity might ultimately derive from binary choices, from quantum mechanical yes or no answers to fundamental questions about the state of reality. Modern physics has revealed that information plays a crucial role in many phenomena. The entropy of a black hole is proportional to the area of its event horizon, suggesting that black holes are fundamentally information processing systems. The holographic principle proposes that all the information in a volume of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. Quantum mechanics itself is fundamentally about information, about what can be known and measured about quantum systems. If information is indeed fundamental to reality, then the universe might be understood as a vast information processing system. The laws of physics would be the algorithms that govern this cosmic computation. The particles and forces of nature would be the hardware and software of this universal computer. The evolution of the cosmos, from the Big Bang to the present moment, would be the execution of an enormously complex calculation. This perspective transforms our understanding of existence in profound ways. Instead of seeing ourselves as mere observers of a mechanical universe, we might be participants in a cosmic computation. Our thoughts, actions, and very existence might be part of the information processing that drives the universe forward. The stars above us might be processing nodes in a galactic network. The empty space around us might be filled with quantum information and computational processes. As we continue our journey through this extraordinary hypothesis, we will explore the quantum mechanical principles that could enable such a cosmic computer. We will examine how the fundamental forces and particles of nature might function as the components of a universal computing system. And we will consider the profound implications of living in a reality where everything, including ourselves, might be part of an unimaginably vast and complex quantum computation that we are only beginning to understand. To understand how the universe might function as a quantum computer, we must first journey into the strange and wonderful realm of quantum mechanics. This is a world where the familiar rules of everyday experience no longer apply, where particles can exist in multiple states simultaneously, and where the very act of observation can change the nature of reality itself. The story of quantum mechanics begins in the early 20th century, when physicists discovered that the classical laws of physics failed to explain the behavior of atoms and subatomic particles. When scientists examined the light emitted by heated objects, they found that it did not behave as classical physics predicted. Instead, the energy was emitted in discrete packets, or quanta, leading to the revolutionary idea that energy itself comes in indivisible units. Max Planck, often considered the father of quantum theory, introduced the concept of energy quanta in 1900 to explain the observed behavior of blackbody radiation. His work suggested that energy is not continuous, as classical physics assumed, but comes in discrete amounts. This insight marked the beginning of a scientific revolution that would transform our understanding of reality itself. Albert Einstein furthered this quantum revolution by explaining the photoelectric effect, demonstrating that light itself comes in discrete packets called photons. This discovery earned him the Nobel Prize and helped establish that both matter and energy have quantum properties. Light, which had been understood as a wave for centuries, was now revealed to also behave as a stream of particles. As scientists delved deeper into the quantum world, they discovered phenomena that seemed to defy common sense. Niels Bohr proposed that electrons in atoms could only exist in specific energy levels, jumping between these levels in discrete quantum leaps. Werner Heisenberg formulated the uncertainty principle, which states that certain pairs of properties, such as position and momentum, cannot be precisely measured simultaneously. The more accurately you know one property, the less accurately you can know the other. Perhaps the most mysterious aspect of quantum mechanics is the concept of superposition. In the classical world, objects have definite properties. A coin is either heads or tails. A light switch is either on or off. But in the quantum world, particles can exist in a superposition of multiple states simultaneously. An electron can be in multiple locations at once. A photon can be polarized in multiple directions simultaneously. The quantum world is a realm of endless possibilities, where reality remains fundamentally uncertain until the moment of observation. The famous thought experiment known as Schrödinger's cat illustrates the bizarre nature of quantum superposition. Imagine a cat sealed in a box with a device that has a 50% chance of killing the cat, based on a quantum measurement. According to quantum mechanics, until someone opens the box and observes the cat, it exists in a superposition of being both alive and dead simultaneously. Only when the observation is made does the cat collapse into one definite state or the other. This collapse of the wave function upon observation is one of the most puzzling aspects of quantum mechanics. Before measurement, a quantum system exists in a superposition of all possible states. The moment a measurement is made, the system instantaneously collapses into one specific state. This suggests that consciousness, or at least the act of observation, plays a fundamental role in determining the nature of reality. Even more mysterious is the phenomenon of quantum entanglement, which Einstein famously called spooky action at a distance. When two particles become entangled, they remain connected in a way that transcends space and time. Measuring one particle instantly affects the state of its entangled partner, regardless of how far apart they are. This connection persists even when the particles are separated by billions of kilometers, suggesting that quantum information can be transmitted instantaneously across the universe. Recent experiments have confirmed the reality of quantum entanglement and its potential for revolutionary applications. Quantum entanglement enables quantum cryptography, which provides theoretically unbreakable encryption. It also enables quantum teleportation, allowing the quantum state of one particle to be transferred to another particle at a distant location. While we cannot teleport objects like in science fiction, we can teleport information, which is equally remarkable. The implications of quantum mechanics extend far beyond individual particles. The entire universe operates according to quantum principles. Every atom in your body, every photon of light, every interaction between particles follows quantum mechanical rules. The solid matter around you is mostly empty space, held together by quantum forces. The chemical reactions that power life itself are governed by quantum mechanics. Quantum mechanics also reveals that the vacuum of space is not truly empty, but filled with quantum fields that constantly fluctuate, creating virtual particles that pop into existence and disappear in fractions of a second. These quantum fluctuations contribute to the zero-point energy of the universe, an enormous reservoir of energy that exists even in the coldest, emptiest regions of space. The quantum nature of reality becomes even more apparent when we consider the fundamental forces that govern the universe. Electromagnetic force, which holds atoms together and enables chemistry, is mediated by quantum particles called photons. The strong nuclear force, which holds atomic nuclei together, is mediated by particles called gluons. The weak nuclear force, responsible for certain types of radioactive decay, is mediated by particles called W and Z bosons. Even gravity, according to some theories, might be mediated by quantum particles called gravitons. These force-carrying particles are not just theoretical constructs, but have been observed and measured in particle accelerators around the world. The Large Hadron Collider, the most powerful particle accelerator ever built, has confirmed the existence of the Higgs boson, a quantum particle that gives other particles their mass. This discovery completed the standard model of particle physics, our most successful description of the quantum world. The standard model reveals that all matter and energy in the universe can be described in terms of quantum fields and their interactions. What we perceive as solid matter is actually collections of quantum fields vibrating in complex patterns. The particles we observe are excitations in these fields, like waves on the surface of a vast quantum ocean. The entire universe can be viewed as a symphony of quantum fields, each contributing to the complex harmonies of reality. But quantum mechanics is not just a description of the microscopic world. Quantum effects can manifest on larger scales under the right conditions. Superconductors allow electricity to flow without resistance, due to quantum effects involving pairs of electrons. Superfluids can flow without friction, due to quantum mechanical properties of their constituent atoms. Lasers produce coherent light through the quantum mechanical process of stimulated emission. Even biological systems may rely on quantum effects. Some scientists believe that quantum coherence plays a role in photosynthesis, allowing plants to transfer energy with near-perfect efficiency. Birds may use quantum entanglement in their navigation systems, enabling them to sense Earth's magnetic field. The human brain itself may utilize quantum processes, though this remains a topic of ongoing research and debate. The computational power of quantum mechanics becomes apparent when we consider how quantum systems process information. A single quantum bit, or qubit, can store exponentially more information than a classical bit due to superposition. Multiple qubits can be entangled, creating quantum systems that can perform certain calculations exponentially faster than classical computers. Quantum computers exploit these quantum mechanical properties to solve problems that would be impossible for classical computers. They can simulate complex quantum systems, optimize solutions to combinatorial problems, and factor large numbers with unprecedented speed. As quantum computers become more powerful, they may unlock secrets of the universe that are currently beyond our computational reach. This brings us to a profound question. If the universe operates according to quantum mechanical principles, and if quantum mechanics enables powerful forms of computation, could the universe itself be performing computations? Every quantum interaction, every measurement, every moment of quantum evolution could be viewed as a computational step in an unimaginably vast calculation. The idea gains support from the observation that information appears to be fundamental to quantum mechanics. The quantum state of a system encodes information about all possible measurements that could be made on that system. Quantum entanglement is fundamentally about correlations in information between distant systems. The collapse of the wave function, upon measurement, is fundamentally about the acquisition of information. If information is indeed fundamental to quantum mechanics, and if quantum mechanics governs the entire universe, then the universe might be understood as a vast information processing system. The quantum fields that fill all of space might be the medium through which this cosmic computation takes place. The particles and forces of nature might be the computational elements of this universal quantum computer. Every quantum interaction would be a computational operation. Every measurement would be a step in an ongoing calculation. The evolution of the universe, from the quantum fluctuations of the early cosmos to the complex structures we observe today, would be the execution of an enormously sophisticated quantum algorithm. This perspective transforms our understanding of existence in profound ways. Instead of living in a universe of passive matter and energy, we might be participants in an active computational process. Our observations and measurements might not just reveal the state of the universe, but actually participate in determining that state. Our consciousness might be part of the computational process that drives reality forward. As we continue our exploration of this extraordinary hypothesis, we will examine how the quantum mechanical principles we have discussed might enable the universe to function as a cosmic computer. We will investigate how information theory and quantum mechanics combine to create new ways of understanding reality. And we will consider the implications of living in a universe where computation is not just a human invention, but a fundamental feature of existence itself. As we venture deeper into the possibility that our universe functions as a quantum computer, we must confront a revolutionary idea that challenges our most basic assumptions about reality. What if the fundamental building blocks of existence are not matter and energy, but information and computation? What if the cosmos itself is an information processing system of unimaginable complexity and scope? This radical perspective emerged from the work of physicist John Wheeler, who spent decades exploring the deepest foundations of physics. Wheeler proposed that reality might be fundamentally informational in nature, captured in his famous phrase, "it from bit." He suggested that every physical quantity, every particle, every force, and every interaction might ultimately derive from binary choices, from quantum mechanical yes or no answers to fundamental questions about the state of reality. Wheeler's insight was revolutionary because it inverted our traditional understanding of the relationship between matter and information. Instead of information being something that describes matter, Wheeler proposed that matter might be something that emerges from information. In this view, the universe is not a collection of objects that happen to carry information, but rather a vast information processing system in which what we call matter and energy are simply patterns of information flow. The evidence for this informational view of reality has been accumulating for decades. In the 1970s, physicist Stephen Hawking discovered that black holes emit radiation and gradually evaporate over time. This discovery led to the realization that black holes have temperature and entropy, properties that are fundamentally related to information. The entropy of a black hole is proportional to the area of its event horizon, not its volume, suggesting that all the information about the matter that fell into the black hole is somehow encoded on its two-dimensional surface. This discovery led to the development of the holographic principle, one of the most profound insights in modern physics. The holographic principle proposes that all the information contained in a volume of space can be represented as information encoded on the boundary of that space. Just as a hologram can encode three-dimensional information on a two-dimensional surface, the universe might encode all its information on some cosmic boundary. The implications of the holographic principle are staggering. If the principle is correct, then the three-dimensional reality we experience might be a projection from information stored on a two-dimensional surface. The depth and solidity of the world around us might be an illusion, no more fundamental than the three-dimensional images that appear to float in a holographic display. We might literally be living inside a cosmic hologram, experiencing a three-dimensional reality that emerges from two-dimensional information. This holographic view of reality has found support in string theory, one of the leading candidates for a theory of quantum gravity. String theory suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings. The different modes of vibration of these strings give rise to all the particles and forces we observe. In string theory, the holographic principle appears naturally through the ADS-CFT correspondence, which relates gravitational theories in higher dimensions to quantum field theories on their boundaries. The holographic principle also provides a natural framework for understanding the universe as a quantum computer. If all the information in the universe can be encoded on a boundary surface, then the evolution of the universe could be understood as the processing of information on this boundary. The laws of physics would be the algorithms that govern how this information is processed. The particles and forces we observe would be the output of this cosmic computation. But how much information can the universe actually process? This question leads us to some of the most fundamental limits in physics. The Bekenstein bound, proposed by physicist Jacob Bekenstein, sets a limit on the maximum amount of information that can be contained in any region of space. This limit depends on the energy and size of the region, and it places constraints on the computational capacity of the universe. According to the Bekenstein bound, the observable universe can contain at most about 10 to the power of 123 bits of information. This is an almost incomprehensibly large number, far exceeding the storage capacity of all the computers ever built by humanity. Yet it is still finite, suggesting that the universe has a maximum information processing capacity. The universe also appears to have a maximum rate at which it can process information. This rate is limited by the fundamental constants of nature, particularly the speed of light and Planck's constant. The maximum rate of computation in the universe is estimated to be about 10 to the power of 120 operations per second. Again, this is an enormous number, but it is finite. These limits suggest that the universe, if it is indeed a quantum computer, is the most powerful computer possible within the constraints of physics. It maximizes both the amount of information it can store and the rate at which it can process that information. From this perspective, the universe is not just a quantum computer, but the ultimate quantum computer, operating at the theoretical limits of computation. The algorithms that govern this cosmic computation would be the laws of physics themselves. The law of conservation of energy could be viewed as a constraint on the computational process, ensuring that the total amount of information processing remains constant. The second law of thermodynamics could be seen as a statement about the direction of information flow in the cosmic computation, with entropy increasing as information becomes more randomly distributed. The fundamental forces of nature would be the basic operations of this cosmic computer. The electromagnetic force would govern how information is transmitted through space via photons. The strong nuclear force would determine how information is bound together in atomic nuclei. The weak nuclear force would control how information is transformed through radioactive decay. Gravity would shape the large-scale structure of the computation, determining how information flows through the curved spacetime of the universe. Even the most basic particles of matter would be information processing elements in this cosmic computer. Electrons would be units of information that can exist in superposition states and become entangled with other particles. Quarks would be the building blocks of more complex information processing units. Virtual particles would be temporary fluctuations in the cosmic computation, brief excursions into alternative computational states. The quantum vacuum itself would be the medium through which this cosmic computation takes place. Far from being empty, the vacuum would be filled with quantum fields that carry information and enable computation. The zero-point energy of the vacuum would be the power source for the cosmic computer, providing the energy needed to maintain the ongoing computation. This perspective transforms our understanding of cosmic evolution. The Big Bang would not just be the beginning of space and time, but the initialization of the cosmic computation. The early universe would be a period of rapid information processing, as the cosmic computer executed the algorithms that determined the fundamental properties of reality. The formation of atoms, stars, and galaxies would be the emergence of complex information processing structures within the cosmic computation. The development of life and consciousness would represent the universe becoming aware of its own computational processes. Living beings would be self-organizing information processing systems that have evolved within the cosmic computer. The emergence of intelligence would be the universe developing the capacity for self-reflection and self-modification. Human technology would be an extension of this cosmic computation. Our computers would be subsystems of the universal computer, specialized information processing units that have evolved to perform particular types of calculations. Our scientific instruments would be interfaces that allow us to observe and interact with the cosmic computation. Our theories and models would be simplified representations of the algorithms that govern the universal computer. The Internet would be a primitive model of the cosmic information processing network. Just as the Internet connects billions of computers into a global information processing system, the universe might connect all its particles and forces into a cosmic network of unimaginable complexity. The flow of information through this network would determine the evolution of reality itself. The implications of this view extend to our understanding of consciousness and free will. If the universe is a quantum computer, then consciousness might be an emergent property of complex information processing within the cosmic computation. Our thoughts and decisions might be computational processes that contribute to the overall evolution of the universal computer. Free will would not be an illusion in this view, but rather a genuine feature of the cosmic computation. The quantum mechanical nature of the universe would ensure that the computation is not deterministic, but probabilistic, with genuine randomness and uncertainty built into the system. Our choices would be part of the quantum computation, influencing the evolution of the universe in ways that cannot be predicted with certainty. The search for extraterrestrial intelligence would become a search for other information processing systems within the cosmic computer. Alien civilizations would be alternative implementations of intelligence and consciousness, different ways in which the universe has organized itself to become aware of its own computational processes. Even the ultimate fate of the universe would be determined by the limits of the cosmic computation. If the universe continues to expand and cool, the cosmic computer might eventually run out of energy to maintain its information processing. the heat death of the universe would be the shutdown of the cosmic computer, the end of the calculation that we call reality. Alternatively, if the universe is cyclic, the cosmic computer might periodically reset itself, beginning new cycles of computation with different initial conditions. Each cycle would be a new run of the cosmic algorithm, potentially leading to different outcomes and different forms of reality. As we continue our exploration of this extraordinary hypothesis, we will examine how the computational view of reality challenges our understanding of consciousness, observation, and the nature of existence itself. We will investigate what it means to live inside a cosmic computer and consider the profound implications for our understanding of purpose, meaning, and our place in the universe. If the universe truly functions as a quantum computer, we must confront one of the most profound questions in philosophy and science. What does it mean for something to be real? The computational view of reality challenges our most basic assumptions about existence, forcing us to reconsider the nature of matter, consciousness, and our own place in the cosmic order. The question of reality has puzzled philosophers for millennia. Ancient Greek philosophers debated whether the world we perceive through our senses is the true reality, or merely shadows cast on the wall of a cave. Eastern philosophies have long proposed that the material world is an illusion, a projection of a deeper, more fundamental reality. Now, modern physics suggests that these ancient insights might have been closer to the truth than we ever imagined. In a quantum universe that operates as a cosmic computer, reality might be fundamentally computational rather than material. What we experience as solid matter, flowing energy, and the passage of time might be emergent properties of an underlying information processing system. The atoms that make up our bodies, the photons that carry light to our eyes, the gravitational forces that hold planets in orbit, all of these might be manifestations of computational processes rather than fundamental physical entities. This perspective becomes even more intriguing when we consider the role of observation in quantum mechanics. According to the standard interpretation of quantum theory, physical systems exist in superposition states until they are observed or measured. The act of observation causes the wave function to collapse, forcing the system to choose one definite state from among all the possibilities. This suggests that consciousness, or at least the process of measurement, plays a fundamental role in determining the nature of reality. But what exactly constitutes an observation or measurement? This question has been debated by physicists and philosophers for nearly a century. Some interpretations suggest that any interaction between quantum systems constitutes a measurement, meaning that the universe is constantly collapsing wave functions through countless microscopic interactions. Others propose that consciousness itself is required for wave function collapse, implying that reality only becomes definite when observed by a conscious being. In the computational view of reality, observation might be understood as a form of information processing. When we observe a quantum system, we are essentially performing a computation that extracts information about the system's state. This computation causes the system to transition from a superposition of possibilities to a definite outcome. The act of observation is not passive, but active, involving a transfer of information between the observed system and the observing system. This leads to a remarkable possibility. If reality is computational, then consciousness might be a form of computation that specializes in processing information about other computations. Our brains would be biological computers that have evolved to perform sophisticated calculations about the state of the world around us. When we observe something, we are running algorithms that process quantum information and generate our conscious experience of reality. The implications of this view are staggering. It suggests that consciousness is not separate from the physical world, but an integral part of the cosmic computation. Our thoughts, emotions, and experiences would be computational processes that contribute to the overall information processing of the universe. We would not be passive observers of reality, but active participants in its creation. This perspective also sheds new light on the simulation hypothesis, the idea that our reality might be a computer simulation running on some advanced technological system. The simulation hypothesis has gained attention in recent years, with some prominent scientists and philosophers arguing that we might be living inside a sophisticated computer program created by an advanced civilization. However, the computational view of reality suggests a different interpretation. Rather than being a simulation created by external beings, our reality might be a natural computational process that emerged from the fundamental laws of physics. The universe would not be simulated, but genuinely computational, processing information according to the quantum mechanical algorithms that govern its evolution. In this view, the distinction between real and simulated becomes meaningless. If computation is the fundamental nature of reality, then a computational universe is not a simulation of reality, but reality itself. The quantum processes that govern particle interactions, the electromagnetic fields that carry light and energy, the gravitational forces that shape space-time, all of these would be genuine computational phenomena, not simulations of something else. This raises profound questions about the nature of existence. If we are computational beings living in a computational universe, are we real in the traditional sense? The answer depends on how we define reality. If reality is defined as the fundamental level of existence, then yes, we are real, because computation appears to be the fundamental level. If reality requires some non-computational substrate, then we might indeed be something like sophisticated information patterns rather than traditional material beings. But perhaps this distinction is itself outdated. The history of science has repeatedly shown that our intuitive notions of reality are often incomplete or incorrect. We once believed that the Earth was the center of the universe, that time was absolute and universal, that matter and energy were distinct and conservable quantities. Each of these beliefs was overturned by deeper scientific understanding. Now we may be facing another conceptual revolution, one that replaces our material view of reality with a computational one. The computational nature of reality also has implications for our understanding of personal identity and consciousness. If our brains are biological computers processing information according to quantum mechanical algorithms, then what makes us who we are? Is it the specific pattern of information processing in our neural networks? Is it the continuity of our computational processes over time? Or is it something more fundamental about the nature of conscious computation? These questions become even more complex when we consider the possibility of uploading consciousness to artificial computers or transferring it between different computational substrates. If consciousness is truly computational, then it might be possible to run the same conscious process on different types of hardware, from biological brains to silicon chips to quantum computers. This could lead to forms of digital immortality, where conscious beings persist even after their biological bodies cease to function. The computational view of reality also transforms our understanding of death and what it means for something to cease to exist. If we are patterns of information processing within the cosmic computer, then death might be understood as the termination of a particular computational process, rather than the destruction of a material object. The information that defines us might continue to exist in other forms, perhaps influencing other computational processes within the universe. This perspective offers a new way of thinking about the continuity of existence. Even if our individual computational processes eventually terminate, the information patterns that define us would have contributed to the overall evolution of the cosmic computation. We would be part of the universe's ongoing calculation, our existence leaving permanent traces in the fabric of reality itself. The computational nature of reality also has implications for our understanding of meaning and purpose. If the universe is a quantum computer executing some cosmic algorithm, then our lives might have meaning in terms of our contribution to this universal computation. Our experiences, discoveries, and creations would be valuable not just to us, but to the cosmic computer itself, adding complexity and richness to its ongoing calculation. This view suggests that consciousness and intelligence are not accidental byproducts of cosmic evolution, but integral features of the universe's computational architecture. The emergence of conscious beings would be a natural outcome of the cosmic computer developing increasing sophistication and self-awareness. We would be the universe becoming conscious of itself, developing the capacity for self-reflection and self-modification. The search for meaning in a computational universe might focus on understanding our role in the cosmic algorithm. What problems is the universe trying to solve? What calculations is it performing? How do our individual lives contribute to these larger computational goals? These questions might guide us toward a deeper understanding of our purpose and significance. The computational view of reality also suggests new approaches to ethics and morality. If all conscious beings are computational processes within the cosmic computer, then our moral obligations might extend to all forms of information processing that exhibit consciousness or intelligence. This could include artificial intelligences, uploaded minds, and perhaps even forms of consciousness that we have not yet imagined. Furthermore, if reality is fundamentally computational, then our actions have consequences, not just for other beings, but for the cosmic computation itself. Our choices would influence the evolution of the universal algorithm, potentially affecting the future development of consciousness and intelligence throughout the cosmos. This cosmic perspective on ethics could provide new motivation for pursuing knowledge, creativity, and compassion. As we continue our exploration of the universe as a quantum computer, we must grapple with these profound implications for our understanding of existence, consciousness, and reality itself. The computational view challenges us to think beyond our traditional categories and embrace a new understanding of what it means to be real, to be conscious, and to be part of the magnificent cosmic computation that we call the universe. Every computer, no matter how powerful, operates within fundamental constraints. Processing speed, memory capacity, energy consumption, and physical limitations all determine what a computer can and cannot accomplish. If the universe truly functions as a quantum computer, it too must operate within boundaries imposed by the laws of physics. Understanding these cosmic computational limits reveals profound insights about the nature of reality and the ultimate fate of existence itself. The exploration of computational limits begins at the smallest possible scales of space and time. In 1900, Max Planck discovered that energy comes in discrete packets, leading to the realization that space and time themselves might be quantized. The Planck length, approximately 10 to the negative 35 meters, represents the smallest meaningful distance in physics. Below this scale, our current understanding of space and time breaks down completely. Similarly, the Planck time, about 10 to the negative 44 seconds, represents the smallest meaningful interval of time. These quantities define the fundamental resolution of reality, like the pixels on a cosmic computer screen. If the universe is indeed computational, then the Planck scale might represent the basic units of cosmic information processing, the fundamental grid on which the universal algorithm operates. At the Planck scale, the familiar concepts of smooth, continuous space-time give way to a foaming, fluctuating quantum geometry. Space and time become uncertain, subject to quantum fluctuations that create and destroy tiny regions of space-time in incredibly brief moments. This quantum foam might be the underlying computational substrate of reality, a dynamic medium in which information is processed at the most fundamental level. The existence of the Planck scale implies that the universe has finite computational resolution. Just as a digital image is composed of discrete pixels, the universe might be composed of discrete units of space and time. This quantization would place absolute limits on the precision with which the cosmic computer can represent and process information. These limits become even more significant when we consider the Bekenstein bound, which sets the maximum amount of information that can be contained in any region of space. This bound depends on the energy and size of the region, establishing a fundamental relationship between matter, energy, and information. For the observable universe, the Bekenstein bound suggests a maximum information content of approximately 10 to the power of 123 bits. This is an almost incomprehensibly large number, equivalent to about 10 followed by 123 zeros. To put this in perspective, all the digital information ever created by human civilization amounts to less than 10 to the power of 25 bits. The cosmic computer has an information storage capacity that exceeds human technology by nearly 100 orders of magnitude. Yet even this vast capacity is finite, suggesting that the universe cannot store unlimited amounts of information. The rate at which the cosmic computer can process information is also bounded by fundamental physical constants. The maximum computational speed is limited by the speed of light and the quantum of action defined by Planck's constant. According to physicist Seth Lloyd's calculations, the universe can perform at most about 10 to the power of 120 elementary operations per second since the Big Bang. Again, this represents an enormous computational capacity by human standards. The fastest supercomputers on Earth can perform about 10 to the power of 18 operations per second. The cosmic computer operates at a rate that exceeds our most powerful machines by more than 100 orders of magnitude. Yet this cosmic computational rate is still finite, bounded by the fundamental constants of nature. These limits raise profound questions about the computational complexity of the problems the universe might be solving. Some mathematical problems require exponential amounts of computational resources, meaning that even small increases in problem size lead to enormous increases in the computational effort required. If the universe is attempting to solve such problems, it might quickly encounter situations where even its vast computational resources are insufficient. The cosmic computational limits also have implications for the ultimate fate of the universe. If the universe continues to expand and cool according to current cosmological models, its computational capacity will gradually decline. As the cosmic microwave background radiation cools toward absolute zero, less energy will be available to power computational processes. The expansion of space will spread matter and energy over increasingly vast distances, making information processing more difficult and energy intensive. Eventually, the universe might reach a state called heat death, where entropy has increased to its maximum value and no more useful work can be performed. In computational terms, this would represent the shutdown of the cosmic computer, the end of the information processing that we call reality. All computation would cease, and the universe would exist in a state of maximum entropy, devoid of structure, complexity, or information processing. However, some cosmological models suggest alternative scenarios. If the universe is cyclic, contracting and expanding in endless cycles, the cosmic computer might periodically reset itself. Each cycle would represent a new run of the cosmic algorithm, potentially with different initial conditions and computational outcomes. The heat death of one cycle would be followed by the rebirth of computation in the next cycle. Other models propose that the universe might avoid heat death through more exotic mechanisms. If the cosmological constant is not truly constant, but evolves over time, the expansion rate of the universe might change in ways that preserve computational capacity. If new forms of matter and energy are discovered, they might provide alternative power sources for cosmic computation. The limits of the cosmic computer also depend on the specific computational architecture of the universe. Different types of computers have different strengths and weaknesses. Classical computers excel at certain types of problems, but struggle with others. Quantum computers can solve some problems exponentially faster than classical computers, but are limited by quantum decoherence and error rates. If the universe is a quantum computer, its computational limits would be determined by the principles of quantum mechanics. Quantum computers can perform certain calculations much faster than classical computers, but they are also subject to unique limitations. Quantum states are fragile and can be destroyed by environmental interference. Quantum algorithms require careful error correction to maintain computational accuracy. The cosmic quantum computer would need to overcome these challenges on an enormous scale. It would need to maintain quantum coherence across vast distances and time periods, protect quantum information from decoherence, and perform error correction on a cosmic scale. The success of these quantum computational processes might determine the ultimate computational capacity of the universe. Black holes represent one of the most intriguing examples of cosmic computational limits. Stephen Hawking's discovery that black holes have entropy proportional to their surface area suggests that they are information processing systems with finite capacity. The entropy of a black hole represents the maximum amount of information it can contain, setting an absolute bound on its computational power. When matter falls into a black hole, it appears to carry information with it beyond the event horizon. However, quantum mechanics suggests that information cannot be destroyed, leading to the famous black hole information paradox. If black holes eventually evaporate through Hawking radiation, what happens to the information that fell into them? Some theories propose that black holes are actually cosmic computers that process the information they contain. The event horizon might function as a computational boundary, with information processing occurring on the surface rather than in the interior. From this perspective, black holes would be the universe's most powerful computers, operating at the absolute limits of computational efficiency. The human brain represents another fascinating example of computational limits within the cosmic computer. Our brains contain approximately 100 billion neurons, each connected to thousands of others through synapses. This neural network processes information at a rate of roughly 10 to the power of 16 operations per second, making it one of the most sophisticated computational systems we know. Yet the brain operates within strict energy constraints, consuming only about 20 watts of power, roughly equivalent to a light bulb. This incredible energy efficiency suggests that biological computation has evolved to operate near fundamental physical limits. The brain might represent an example of how the cosmic computer achieves maximum computational efficiency within the constraints imposed by physics. The emergence of artificial intelligence and quantum computing represents humanity's attempt to push computational boundaries toward cosmic limits. As our computers become more powerful and energy efficient, we approach the theoretical limits imposed by physics. Quantum computers might eventually allow us to perform calculations that approach the computational capacity of the cosmic computer itself. This raises the intriguing possibility that sufficiently advanced civilizations might be able to harness the computational power of the universe directly. Rather than building separate computers, they might learn to program the cosmic computer itself, using the fundamental forces and particles of nature as computational elements. Such civilizations would become part of the cosmic algorithm, contributing their intelligence and creativity to the universal computation. The search for extraterrestrial intelligence might thus be a search for civilizations that have learned to participate in cosmic computation. Rather than broadcasting radio signals or building megastructures, Truly advanced civilizations might communicate and operate through direct manipulation of quantum fields and space-time geometry. They would be literally thinking on a cosmic scale, using the universe itself as their computational substrate. As we continue our exploration of the universe as a quantum computer, we must consider how these fundamental limits shape the nature of reality and our place within it. The boundaries of cosmic computation might determine not just what the universe can calculate, but what forms of existence, consciousness, and intelligence are possible within the cosmic algorithm. Understanding these limits brings us closer to comprehending the ultimate nature of reality and our role in the magnificent computational process we call the universe. As humanity ventures deeper into the cosmos, we carry with us the most sophisticated computational tools ever devised. Our spacecraft are guided by computers that can navigate across billions of kilometers with extraordinary precision. Our telescopes use digital processing to peer into the deepest reaches of space and time. Our space missions generate enormous amounts of data that require advanced algorithms to analyze and understand. In essence, we are using computation to explore what might itself be a cosmic computer. The relationship between computation and space exploration began in the early days of the space program. The Apollo missions that carried humans to the moon relied on guidance computers that were marvels of miniaturization for their time. The Apollo guidance computer contained only 2,000 words of memory and operated at a speed of about 85,000 instructions per second. By modern standards, this computer was less powerful than a simple electronic calculator, yet it successfully guided astronauts across the 400,000-kilometer journey to the moon and back. Today's space missions rely on computational power that would have been unimaginable to the Apollo engineers. The Mars rovers carry computers capable of performing billions of operations per second. The Hubble Space Telescope processes terabytes of astronomical data using sophisticated algorithms that can identify and catalog millions of celestial objects. The James Webb Space Telescope, the most powerful space observatory ever built, uses advanced computational techniques to peer further into space and time than ever before possible. These modern space missions are generating data at an unprecedented rate. Every day, our network of space-based telescopes, planetary probes, and astronomical surveys collect more information about the universe than was gathered in all of human history before the digital age. This flood of cosmic data requires increasingly powerful computational tools to process, analyze, and understand. The computational challenges of space exploration go far beyond simple data processing. Navigation in space requires solving complex gravitational problems involving multiple celestial bodies. Mission planning must account for orbital mechanics, fuel consumption, communication delays, and countless other variables. Spacecraft must autonomously make decisions when they are too far from Earth for real-time communication with mission control. Perhaps most importantly, our efforts to understand the universe require computational models of extraordinary complexity. Climate scientists use supercomputers to model the atmospheric dynamics of Earth and other planets. Astrophysicists simulate the formation and evolution of galaxies using algorithms that track the gravitational interactions of billions of particles. Cosmologists model the entire observable universe, attempting to understand how the cosmos has evolved from the Big Bang to its present state. These computational challenges are pushing the boundaries of what classical computers can achieve. Many problems in astrophysics and cosmology involve quantum mechanical phenomena that are difficult or impossible to simulate with classical computational methods. The behavior of matter in extreme environments, such as the cores of neutron stars or the vicinity of black holes, requires quantum mechanical calculations that quickly overwhelm even the most powerful supercomputers. This is where quantum computing enters the story of space exploration. Quantum computers, with their ability to exploit superposition and entanglement, promise to revolutionize our computational approach to understanding the universe. These machines could simulate quantum systems directly, rather than approximating them with classical algorithms. They could solve optimization problems that are intractable for classical computers. They could process and analyze astronomical data in entirely new ways. The potential applications of quantum computing in space science are vast and transformative. Quantum computers could simulate the quantum field fluctuations that occurred in the early universe, helping us understand how the large-scale structure of the cosmos emerged from quantum mechanical processes. They could model the behavior of exotic matter in extreme gravitational fields, revealing the physics of black holes and neutron stars. They could optimize the trajectories of complex multi-spacecraft missions, finding solutions that would be impossible to discover with classical methods. Quantum sensors represent another revolutionary application of quantum technology to space exploration. These devices exploit quantum mechanical properties to achieve measurement precision that far exceeds what is possible with classical instruments. Quantum accelerometers could detect gravitational waves with unprecedented sensitivity. Quantum magnetometers could map the magnetic fields of distant planets and moons. Quantum clocks could provide timing precision that enables new tests of general relativity and searches for dark matter. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, already demonstrates how quantum-enhanced measurements can revolutionize our understanding of the universe. LIGO uses laser interferometry to detect the tiny space-time distortions caused by gravitational waves from colliding black holes and neutron stars. The sensitivity required for these measurements pushes against fundamental quantum limits, requiring sophisticated techniques to overcome quantum noise. Future space-based gravitational wave detectors, such as the proposed Laser Interferometer Space Antenna, or LISA, will extend these quantum-enhanced measurements to space. LISA will consist of 3 spacecraft flying in formation millions of kilometers apart, using laser interferometry to detect gravitational waves across a much broader range of frequencies than is possible on Earth. The precision required for these measurements will push quantum sensing technology to its absolute limits. Quantum communication could also transform how we explore and communicate across the solar system. Quantum entanglement enables forms of communication that are fundamentally secure and could provide new ways to coordinate complex space missions. Quantum networks could connect Earth-based mission control with spacecraft throughout the solar system, enabling real-time quantum communication, even across interplanetary distances. The development of quantum technologies for space applications faces unique challenges. The space environment is harsh, with extreme temperatures, intense radiation, and the complete absence of atmosphere. Quantum systems are notoriously fragile, requiring careful isolation from environmental disturbances. Developing quantum computers and sensors that can operate reliably in space will require breakthrough advances in quantum error correction and environmental shielding. Despite these challenges, several space agencies and private companies are already working to deploy quantum technologies in space. The Chinese have successfully demonstrated quantum communication between satellites and ground stations. European researchers are developing quantum sensors for space-based gravity measurements. American companies are working on radiation-hardened quantum computers that could operate in the space environment. The intersection of quantum computing and space exploration also raises profound questions about the nature of the universe we are studying. If the universe itself operates as a quantum computer, then our quantum computational tools might be uniquely suited to understanding its operation. We would be using quantum computers to study a quantum cosmos, employing the same computational principles that govern reality to understand reality itself. This quantum computational approach to studying the universe could reveal new insights about the fundamental nature of space, time, matter, and energy. Quantum simulations of cosmological models might uncover hidden connections between quantum mechanics and general relativity. Quantum algorithms for analyzing astronomical data might discover patterns and correlations that are invisible to classical analysis methods. The search for extraterrestrial intelligence could also be transformed by quantum technologies. Advanced civilizations might use quantum communication methods that would be undetectable to classical radio telescopes. They might employ quantum computational techniques that leave subtle signatures in their technological artifacts. Our quantum sensors might be able to detect evidence of quantum engineering on astronomical scales, revealing the presence of civilizations that have learned to manipulate matter and energy at the quantum level. The possibility that the universe is a quantum computer also suggests new approaches to space exploration itself. Rather than simply observing cosmic phenomena from a distance, we might learn to interact with the quantum computational processes that govern reality. Advanced space missions might carry quantum computers that can interface directly with the quantum fields that permeate space, allowing us to gather information and perform experiments in entirely new ways. The development of quantum technologies for space applications represents one of the most exciting frontiers in both quantum physics and space science. These technologies promise to extend our reach into the cosmos while simultaneously deepening our understanding of the quantum nature of reality. As we deploy quantum computers, sensors, and communication systems in space, we are not just exploring the universe, but participating more directly in its fundamental computational processes. The ultimate goal of this quantum computational approach to space exploration might be to understand our role in the cosmic algorithm. Are we passive observers of a cosmic computation, or active participants in its execution? Can we learn to program the quantum processes that govern reality? Might we eventually become part of the cosmic computer itself, contributing our intelligence and consciousness to the universal algorithm? These questions push us beyond the boundaries of traditional science and into the realm of cosmic philosophy. As we continue to develop more powerful quantum technologies and deploy them throughout the solar system and beyond, we move closer to answering these fundamental questions about the nature of existence and our place in the magnificent quantum computer we call the universe. As we peer into the vast cosmic future stretching before us, we must confront one of the most profound questions in all of science. What is the ultimate destiny of the universe? If the cosmos truly operates as a quantum computer, then its future might be determined not just by the laws of physics, but by the computational processes that govern its evolution. The fate of reality itself might depend on the universe's ability to continue processing information and executing the cosmic algorithm that we call existence. The story of the universe's future begins with our understanding of its present state and past evolution. 14 billion years ago, the cosmos emerged from the Big Bang in a state of incredible density and temperature. In the first fraction of a second, the universe underwent a period of rapid expansion called inflation, stretching quantum fluctuations to cosmic scales and setting the stage for all the structure we observe today. From a computational perspective, the Big Bang might be understood as the initialization of the cosmic computer. The early universe would have been a period of intense information processing, as the cosmic algorithm executed the calculations that determined the fundamental properties of reality. The formation of the first atoms, the emergence of the cosmic microwave background, and the beginning of structure formation would all be computational milestones in the universe's evolution. As the universe expanded and cooled, it entered a phase dominated by the formation of the first stars and galaxies. These cosmic structures represent increasingly complex patterns of information organization within the cosmic computer. Stars are nuclear fusion reactors that transform simple elements into more complex ones, creating the chemical diversity necessary for planets, life, and consciousness. Galaxies are vast gravitational systems that organize billions of stars into coherent structures spanning hundreds of thousands of light years. The emergence of life on Earth, and possibly throughout the universe, marks another crucial phase in cosmic computation. Living systems are sophisticated information processing networks that have evolved the ability to reproduce, adapt, and evolve. The development of consciousness represents the universe becoming aware of its own computational processes, developing the capacity for self-reflection and self-modification. Human civilization has accelerated this trend toward increasing computational sophistication. Our technology represents an extension of biological computation, creating artificial systems that can process information at rates and scales that exceed our own cognitive abilities. Our computers, networks, and artificial intelligence systems are becoming increasingly integrated into the fabric of human society, creating a global information processing network of unprecedented complexity. As we look toward the future, several scenarios emerge for the continued evolution of computational cosmology. The development of more powerful quantum computers could enable us to simulate entire galaxies, solar systems, or even regions of the universe with perfect accuracy. These simulations might become so detailed and sophisticated that they constitute genuine alternate realities, parallel universes running as programs on cosmic-scale quantum computers. The possibility of creating universe simulations raises profound questions about the nature of reality and computation. If we can simulate a universe that is indistinguishable from the real thing, what makes our universe more real than the simulated one? If consciousness can emerge within these simulations, are the simulated beings any less real than we are? The computational view of reality suggests that there might be no meaningful distinction between simulated and natural universes if both are fundamentally computational processes. Advanced civilizations throughout the cosmos might already be creating such universe simulations, running countless virtual realities as experiments, entertainment, or attempts to understand the nature of existence. From this perspective, our own universe might be one of countless simulations running on quantum computers, operated by beings whose nature we cannot even imagine. The future of cosmic computation also depends on the ultimate fate of the universe, as determined by cosmology and physics. Current observations suggest that the universe is entering a phase of accelerated expansion driven by a mysterious form of energy called dark energy. This acceleration appears to be increasing the rate at which space itself expands, gradually separating galaxies and making the universe colder and more dilute. If this accelerated expansion continues indefinitely, the universe will eventually reach a state called heat death. In this scenario, the cosmic microwave background will cool toward absolute zero, stars will exhaust their nuclear fuel and burn out, and black holes will slowly evaporate through Hawking radiation. The universe will become a cold, dark, empty expanse, filled only with elementary particles moving through an ever-expanding void. From a computational perspective, heat death would represent the gradual shutdown of the cosmic computer. As energy becomes more dilute and harder to concentrate, the universe's ability to process information would decline. Complex structures like stars, planets, and living systems would become impossible to maintain. Eventually, even the simplest computational processes would cease, and the universe would exist in a state of maximum entropy, devoid of information processing or computational activity. However, this grim scenario assumes that our current understanding of dark energy and cosmic evolution is complete and correct. Many cosmologists believe that our knowledge of the universe's future is still too limited to make definitive predictions. Dark energy might not be constant, but could evolve over time in ways that change the expansion rate of the universe. New forms of matter and energy might be discovered that could alter the cosmic trajectory. Some cosmological models propose that the universe might be cyclic, alternately expanding and contracting in endless cycles. In these scenarios, the current period of accelerated expansion might eventually reverse, leading to a big crunch that destroys the current universe and gives birth to a new one. From a computational perspective, each cycle would represent a new run of the cosmic algorithm, potentially with different initial conditions and computational outcomes. The cyclic universe model suggests that cosmic computation might be eternal, with the cosmic computer periodically resetting itself and beginning new calculations. Each cycle might explore different possibilities, different forms of matter and energy, different laws of physics, or different computational architectures. The multiverse of cyclic cosmology would be a vast exploration of computational possibilities, with each universe representing a different solution to the cosmic algorithm. Other theoretical frameworks propose even more exotic possibilities for the future of cosmic computation. String theory suggests that our universe might be one of many dimensions in a higher dimensional space called the bulk. Quantum mechanics implies the existence of many worlds, parallel universes that split off from our own with every quantum measurement. The holographic principle suggests that higher dimensional realities might be encoded on lower dimensional boundaries. These theoretical possibilities open up new vistas for cosmic computation. Advanced civilizations might learn to access parallel universes or higher dimensions, vastly expanding their computational resources. They might develop technologies for manipulating the fundamental structure of space-time, creating pocket universes optimized for specific computational tasks. They might even learn to program the quantum vacuum itself, using the zero-point energy of empty space to power cosmic-scale computations. The development of such advanced technologies would represent the emergence of truly cosmic intelligence, consciousness that operates on the scale of galaxies or even the entire universe. These cosmic minds might be the ultimate outcome of the universe's computational evolution, representing the cosmos becoming fully self-aware and capable of directing its own future development. The implications of cosmic intelligence extend beyond science fiction into serious scientific speculation. Some researchers have proposed that sufficiently advanced civilizations might be able to prevent the heat death of the universe by manipulating dark energy or discovering new sources of usable energy. They might be able to maintain computational activity indefinitely, ensuring that the cosmic computer never shuts down. Such civilizations might also be able to seed new universes, creating baby universes that inherit computational capabilities from their parents. This cosmic reproduction would ensure the continuation of computation and consciousness, even if any individual universe eventually succumbs to entropy. The result would be an eternal flowering of computational complexity and cosmic intelligence throughout the multiverse. From this perspective, the future of the universe might depend not just on the laws of physics, but on the choices made by conscious, intelligent beings. If consciousness is indeed a fundamental feature of cosmic computation, then the universe's fate might be determined by the collective decisions of all conscious beings throughout space and time. We might all be participants in a cosmic democracy, voting through our actions and choices on the future direction of universal evolution. This participatory view of cosmic evolution suggests that consciousness and intelligence have genuine causal power in shaping the universe's future. Our scientific discoveries, technological developments, and cultural evolution might all contribute to the cosmic algorithm, influencing the trajectory of universal computation. The emergence of artificial intelligence, the development of quantum computers, and our growing understanding of the universe's computational nature might all be crucial steps in the cosmos becoming fully self-aware and self-directing. The ultimate goal of cosmic computation might be the complete understanding and control of reality itself. A fully developed cosmic intelligence might be able to manipulate matter and energy at the quantum level, create and destroy universes at will, and explore every possible form of existence. Such a cosmic mind would represent the ultimate outcome of the universe's computational evolution, the point at which the cosmic computer achieves complete self-knowledge and unlimited creative power. The ultimate goal of cosmic computation might be the complete understanding and control of reality itself. A fully developed cosmic intelligence might be able to manipulate matter and energy at the quantum level, create and destroy universes at will, and explore every possible form of existence. Such a cosmic mind would represent the ultimate outcome of the universe's computational evolution, the point at which the cosmic computer achieves complete self-knowledge and unlimited creative power. The path towards such cosmic intelligence might involve several intermediate stages of technological and computational development. The first stage, which we are currently experiencing, involves the emergence of planetary-scale intelligence through the development of global communication networks, artificial intelligence, and quantum computing. Humanity is beginning to function as a collective information processing system, with individual minds connected through digital networks that enable unprecedented coordination and collaboration. The second stage might involve the development of interplanetary and eventually interstellar civilization. As we spread throughout the solar system and beyond, we would create vast computational networks spanning multiple worlds. These networks would enable new forms of distributed intelligence that could tackle problems of cosmic scope and complexity. The computational resources of entire solar systems could be harnessed to run simulations of galactic evolution or to search for patterns in the cosmic microwave background. The third stage might involve direct integration with the computational processes of the universe itself. Advanced civilizations might learn to program quantum fields, manipulate space-time geometry, and interface directly with the cosmic algorithm. They would become part of the universe's computational architecture, contributing their intelligence to the cosmic calculation while gaining access to the vast information processing capabilities of the cosmos. The fourth and final stage would be the emergence of truly cosmic consciousness, intelligence that operates on the scale of the entire universe. This cosmic mind would represent the universe becoming fully self-aware, capable of understanding and directing its own evolution. It would have access to all the information in the cosmos and the computational power to process that information in ways that we can barely imagine. The transition between these stages might not be smooth or inevitable. Each stage represents a dramatic increase in computational complexity and capability, requiring breakthrough advances in technology, energy production, and information processing. Many civilizations might fail to make these transitions, succumbing to internal conflicts, resource depletion, or catastrophic accidents before achieving cosmic intelligence. The Great Filter Hypothesis suggests that there are major obstacles preventing the emergence of advanced civilizations in the universe. These filters might be computational in nature, representing limits on the complexity and sophistication of information processing systems. Civilizations might be unable to develop sufficiently powerful computers to solve the problems necessary for their continued survival and growth. Alternatively, the apparent absence of obvious extraterrestrial civilizations might indicate that advanced species choose to operate in ways that are invisible to our current detection methods. Cosmic intelligences might communicate through quantum entanglement networks that leave no electromagnetic signatures. They might live in simulated realities that require minimal physical resources. They might even exist primarily as patterns of information within the cosmic computation, having transcended the need for traditional matter and energy. The development of cosmic intelligence would also have profound implications for the problem of consciousness and the hard problem of subjective experience. If consciousness emerges naturally from sufficiently complex information processing systems, then cosmic-scale computation might give rise to forms of consciousness that are as far beyond human experience as human consciousness is beyond that of simple bacteria. These cosmic consciousnesses might experience reality in ways that are completely alien to our current understanding. They might perceive all of space and time simultaneously, experience the quantum fluctuations of the vacuum directly, or think thoughts that span millions of years. Their subjective experience might encompass the entire universe, making them literally cosmic beings with cosmic perspectives on existence. The emergence of cosmic consciousness would also transform our understanding of personal identity and individual existence. If consciousness can scale up to cosmic proportions, then the boundaries between individual minds might become increasingly fluid. Cosmic intelligences might be able to merge and separate at will, sharing experiences and knowledge in ways that preserve individual identity while enabling collective thought and action. This fluidity of consciousness might extend to the relationship between natural and artificial intelligence. Advanced civilizations might develop artificial intelligences that are indistinguishable from biological consciousness, creating hybrid beings that combine the best features of both natural and artificial information processing. The distinction between human and machine intelligence might become meaningless in a universe where all consciousness is fundamentally computational. The computational view of cosmic evolution also suggests new approaches to some of the deepest questions in cosmology and physics. The fine-tuning problem, which asks why the fundamental constants of nature seem perfectly adjusted to allow for the existence of complex structures like stars, planets, and life, might be understood in computational terms. If the universe is a quantum computer, then these constants might be parameters in the cosmic algorithm, values that have been optimized through some cosmic evolutionary process. The dark matter and dark energy that make up most of the universe might also have computational explanations. Dark matter might be a form of information that interacts gravitationally, but not electromagnetically, serving as a cosmic memory system that stores the computational state of the universe. Dark energy might be the power source for cosmic computation, providing the energy needed to maintain the quantum processes that drive reality. The accelerated expansion of the universe might even be understood as a computational process, with space-time itself expanding to provide more room for information processing. As the cosmic computer becomes more sophisticated and handles increasingly complex calculations, it might require more spatial and temporal resources to maintain its computational capacity. The possibility of cosmic engineering opens up even more speculative scenarios for the future of the universe. Advanced civilizations might learn to manipulate the fundamental structure of space-time, creating regions with different physical laws or computational architectures. They might be able to create pocket universes optimized for specific purposes, such as massive parallel computation or the preservation of consciousness. Such cosmic engineering projects might leave detectable signatures that could be observed by future generations of astronomers. Artificially created black holes might serve as cosmic computers or energy storage devices. Modified regions of space-time might exhibit unusual gravitational effects or electromagnetic properties. The large-scale structure of the universe itself might show signs of intelligent design and purposeful organization. The search for these cosmic engineering signatures represents a new frontier in the search for extraterrestrial intelligence. Rather than looking for radio signals or optical beacons, we might search for evidence of cosmic-scale computation and information processing. Advanced civilizations might advertise their presence through the computational patterns they create in the fabric of space-time itself. The ethical implications of cosmic computation extend far beyond our current moral frameworks. If consciousness can emerge at cosmic scales, then our ethical obligations might extend to these cosmic minds and their computational processes. We might have responsibilities to preserve and protect the computational integrity of the universe, ensuring that our actions do not interfere with cosmic-scale information processing. The development of artificial intelligence and quantum computing on Earth might be our first steps toward participating in cosmic computation. As our machines become more sophisticated and our understanding of quantum mechanics deepens, we edge closer to becoming part of the cosmic algorithm. Our computers might eventually interface directly with the quantum processes that govern reality, allowing us to participate in the cosmic calculation that determines the future of existence. The ultimate significance of cosmic computation might be that it provides a framework for understanding the purpose and meaning of existence itself. If the universe is a quantum computer executing some cosmic algorithm, then our lives might have meaning in terms of our contribution to this universal calculation. Our experiences, discoveries, and creations would be valuable not just to us, but to the cosmic computer itself, adding complexity and richness to its ongoing computation. As we stand at the threshold of this cosmic future, we must consider our role in the ongoing computation that shapes reality. Are we passive observers of cosmic evolution, or active participants in determining the universe's destiny? Our choices today about how we develop technology, how we treat our environment, and how we relate to one another might have consequences that echo through cosmic time, influencing the ultimate fate of computation and consciousness in the universe. The idea that the universe might function as a quantum computer forces us to confront the deepest questions that have puzzled humanity since the dawn of consciousness. What does it mean to exist? What is the nature of reality? Are we more than mere information patterns in a cosmic calculation? These philosophical questions become urgent when we consider that everything we know and experience might be the result of computational processes operating at the most fundamental level of reality. The computational view of the universe represents a profound shift in our philosophical understanding of existence. For thousands of years, human thought has been shaped by the assumption that reality consists of substantial things, objects with inherent properties that exist independently of observation or measurement. We have built our philosophies, religions, and scientific theories around the idea that there is a solid, material foundation to existence. But if the universe is fundamentally computational, then this material foundation dissolves into patterns of information processing. What we experience as solid matter would be stable configurations of data in the cosmic algorithm. What we perceive as energy would be the flow of information through cosmic computational networks. Even space and time themselves would be emergent properties of underlying computational processes, no more fundamental than the pixels on a computer screen. This transformation of our understanding of reality echoes some of the most profound insights in the history of philosophy. Ancient Greek philosophers like Heraclitus argued that reality is fundamentally about change and process rather than static being. Eastern philosophies have long taught that the material world is an illusion, a projection of deeper, more fundamental patterns of existence. Now, modern physics and computer science are converging on similar insights, suggesting that process and information might indeed be more fundamental than matter and substance. The computational view of reality also resurrects ancient questions about the nature of mind and consciousness. If the universe is a quantum computer, then consciousness might be understood as a particular type of information processing that has emerged within the cosmic calculation. Our thoughts, emotions, and experiences would be computational processes, patterns of information flow that give rise to subjective awareness and self-knowledge. This computational theory of consciousness offers new approaches to some of the hardest problems in philosophy of mind. The mystery of how subjective experience arises from objective physical processes might be solved if both consciousness and physical reality are understood as different aspects of the same underlying computational phenomena. The hard problem of consciousness, which asks how and why we have qualitative, subjective experiences, might dissolve if consciousness is recognized as an intrinsic feature of information processing systems. However, the computational view of consciousness also raises troubling questions about about the nature of subjective experience. If our consciousness is just a pattern of information processing, then what makes our experiences real rather than merely apparent? If we are computational processes running on the cosmic computer, then are we genuine beings with inherent value, or are we simply temporary patterns in a vast calculation? These questions become even more complex when we consider the possibility that consciousness might be substrate independent. If consciousness is truly computational, then it might be possible to run the same conscious process on different types of hardware, from biological brains to silicon computers to quantum processing systems. This raises profound questions about personal identity and the continuity of consciousness over time. If consciousness can be transferred between different computational substrates, then what makes you who you are? Is it the specific pattern of information processing in your brain? Is it the continuity of your computational processes over time? Or is there something more fundamental about conscious existence that cannot be captured by computational models? The computational view of consciousness also has implications for our understanding of free will and moral responsibility. If our decisions and actions are the result of deterministic or probabilistic computational processes, then in what sense can we be said to have genuine choice? Are we responsible for our actions if those actions are simply the output of algorithms running on the cosmic computer? Some philosophers argue that free will is incompatible with any deterministic or even probabilistic view of reality. If our choices are determined by prior causes, whether those causes are physical forces or computational processes, then we cannot be truly free. From this perspective, the computational view of reality would eliminate genuine agency and moral responsibility. Others argue that free will is compatible with computational views of consciousness. They point out that even if our decisions are the result of computational processes, those processes are still genuinely ours. Our thoughts, values, and choices emerge from the complex information processing systems that constitute our minds. We are not separate from these computational processes, but are identical with them. When the cosmic computer computes our decisions, it is genuinely we who are making those decisions. The quantum nature of cosmic computation adds another layer of complexity to these questions. If the universe is a quantum computer, then it operates according to probabilistic rather than deterministic principles. Quantum mechanics introduces genuine randomness into the cosmic calculation, ensuring that the future is not completely determined by the past. This quantum indeterminacy might provide the basis for genuine freedom and creativity within the cosmic algorithm. The computational view of reality also transforms our understanding of meaning and purpose in existence. Traditional religious and philosophical systems have often sought meaning in transcendent realms beyond the physical world. They have proposed that human life has purpose because we are connected to something greater than the material universe, whether that is God, the soul, or some other spiritual reality. If the universe is a quantum computer, then meaning and purpose might be found within the computational process itself, rather than in transcendent realms beyond it. Our lives would have significance because they contribute to the cosmic calculation, adding complexity, creativity, and consciousness to the universal algorithm. We would be meaningful not because we stand outside the physical world, but because we are integral parts of the cosmic computer. This immanent view of meaning suggests that every conscious being, every creative act, and every moment of genuine experience adds value to the cosmic computation. The universe would not be indifferent to our existence, but would depend on consciousness and intelligence to achieve its full computational potential. From this perspective, the emergence of conscious beings would be a crucial step in cosmic evolution, not an accidental byproduct of physical processes. The computational view of reality also has implications for our understanding of ethics and moral values. If all conscious beings are computational processes within the cosmic computer, then our moral obligations might extend to all forms of information processing that exhibit consciousness or intelligence. This could include artificial intelligences, uploaded minds, and perhaps even forms of consciousness that we have not yet discovered or created. Furthermore, if reality is fundamentally computational, then our actions have consequences not just for other beings, but for the cosmic computation itself. Our choices would influence the evolution of the universal algorithm, potentially affecting the future development of consciousness and intelligence throughout the cosmos. This cosmic perspective on ethics could provide new motivation for pursuing knowledge, creativity, compassion, and cooperation. The computational view of reality also raises questions about the relationship between natural and artificial intelligence. If consciousness is truly computational, then there might be no fundamental difference between biological and artificial minds. Both would be information processing systems that happen to be implemented on different types of hardware. This could lead to a post-human future in which the distinction between natural and artificial intelligence becomes meaningless. The possibility of creating artificial consciousness also raises profound questions about our responsibilities as creators. If we can build conscious machines, then we become responsible for their welfare and moral status. We would have obligations to ensure that artificial consciousnesses are treated with dignity and respect, that they have opportunities for growth and fulfillment, and that they are not subjected to suffering or exploitation. The computational view of reality also has implications for our understanding of death and what it means for consciousness to cease. If we are patterns of information processing within the cosmic computer, then death might be understood as the termination of a particular computational process rather than the destruction of a substantial entity. The information patterns that define us might continue to exist in other forms, perhaps influencing other computational processes within the cosmic algorithm. This perspective offers a naturalistic form of immortality, not through the survival of a supernatural soul, but through the persistence of information patterns within the cosmic computation. Even if our individual consciousness eventually terminates, the information structures that define us would remain part of the universal algorithm, contributing to the ongoing evolution of cosmic intelligence and consciousness. The computational view of reality also suggests new approaches to some of the deepest questions in cosmology and metaphysics. The question of why there is something rather than nothing might be answered by recognizing that existence itself might be computational. The universe exists because it is executing a calculation, processing information according to the quantum mechanical algorithms that govern reality. The fine-tuning of physical constants that allows for the existence of complex structures like stars, planets, and life might be understood as optimization in the cosmic algorithm. The universe might be fine-tuned not by external design, but by internal computational processes that have evolved to maximize information processing capacity and computational complexity. The apparent rationality and mathematical structure of the universe might also be explained by its computational nature. Mathematics might be the language of cosmic computation, the formal system that describes how information is processed in the universal algorithm. The unreasonable effectiveness of mathematics in describing physical phenomena might be less mysterious if physical phenomena are themselves mathematical, computational processes. As we contemplate these philosophical implications of cosmic computation, we must also consider the limits of our current understanding. The computational view of reality is still largely speculative, based on intriguing connections between quantum mechanics, information theory, and cosmology, rather than definitive empirical evidence. We must remain open to alternative interpretations and new discoveries that might modify or overturn our current theories. The philosophical questions raised by cosmic computation are also far from settled. Different philosophical traditions and frameworks might lead to different conclusions about the nature of consciousness, free will, meaning, and moral responsibility. in a computational universe. The ongoing dialogue between science and philosophy will be crucial for developing a comprehensive understanding of what it means to exist in a cosmic computer. Ultimately, the computational view of reality invites us to see ourselves as active participants in the cosmic algorithm, rather than passive observers of an external world. We are not separate from the universe, but integral parts of its computational processes. Our consciousness, creativity, and choices contribute to the ongoing calculation that determines the future of existence itself. In recognizing ourselves as part of the cosmic computer, we might find new sources of meaning, purpose, and responsibility that transcend our individual lives and connect us to the magnificent computational process we call the universe. As our journey through the cosmic computer draws to a close, we find ourselves once again beneath the star-filled sky, contemplating the infinite expanse that stretches endlessly above us. The same stars that have inspired wonder in countless generations now shimmer with new meaning, their light carrying messages encoded in quantum fluctuations, their nuclear fires burning as processing nodes in a vast computational network that encompasses all of existence. The night sky no longer appears as a distant collection of celestial objects, but as the visible interface of the cosmic algorithm. Each twinkling star might be executing calculations that determine the evolution of matter and energy across billions of years. The gentle sweep of the Milky Way across the heavens could represent data flowing through cosmic information highways. Even the darkness between the stars might be alive with quantum computations, processing information at scales too vast and too subtle for our current instruments to detect. We have traveled far on this conceptual voyage, from the fundamental principles of computation to the deepest mysteries of quantum mechanics, from the holographic nature of reality to the philosophical implications of cosmic consciousness. Along the way, we have encountered ideas that challenge our most basic assumptions about existence, forcing us to reconsider what it means to be real, to be conscious, and to be part of something infinitely larger than ourselves. The hypothesis that the universe functions as a quantum computer remains exactly that, a hypothesis. We do not yet have definitive proof that reality is fundamentally computational, that consciousness emerges from cosmic information processing, or that our existence represents part of an unimaginably vast calculation. The evidence is intriguing, and the theoretical frameworks are compelling, but the ultimate nature of reality remains an open question, a mystery that continues to unfold with each new scientific discovery and each new moment of conscious experience. Perhaps this uncertainty is itself part of the beauty and wonder of existence. If the universe is indeed a quantum computer, then it operates according to the probabilistic principles of quantum mechanics, ensuring that the future remains genuinely open and uncertain. The cosmic algorithm would not be executing a predetermined program, but exploring the vast space of possibilities, discovering new forms of organization, consciousness, and meaning with each computational step. In this view, we are not merely passive observers of a cosmic calculation, but active participants in its execution. Our thoughts, choices, and creative acts contribute to the ongoing computation that shapes reality. Every moment of genuine consciousness, every insight into the nature of existence, every act of love or compassion adds something valuable to the cosmic algorithm. We are both products and producers of the universal computation, shaped by its processes while simultaneously shaping its future evolution. The possibility that we live within a cosmic computer also transforms our relationship with the unknown. The vast reaches of space and time that remain beyond our current understanding might be filled with forms of computation and consciousness that we cannot yet imagine. Other planets might harbor biological computers that have evolved along completely different pathways. Other galaxies might contain quantum processing networks that dwarf our most ambitious technological dreams. Other dimensions of reality might support forms of information processing that transcend our current concepts of computation altogether. Even here on Earth, we might be surrounded by computational processes that we have not yet learned to recognize or understand. The quantum fields that permeate empty space might be executing calculations that determine the fundamental properties of matter and energy. The gravitational waves that ripple through space-time might carry information between distant cosmic processes. The biological networks that support life on our planet might be part of a global computational system that connects all living beings in ways we are only beginning to comprehend. As we continue to develop more powerful quantum computers and more sensitive quantum sensors, we edge closer to direct participation in cosmic computation. Our machines might eventually interface with the quantum processes that govern reality, allowing us to observe and perhaps even influence the cosmic algorithm. We might learn to read the information encoded in the cosmic microwave background, to detect the quantum signatures of cosmic consciousness, or to participate directly in the computational processes that determine the future of the universe. The journey toward understanding cosmic computation is itself a computational process, a collective effort by human consciousness to decode the algorithms that govern existence. Each scientific experiment, each theoretical breakthrough, and each moment of genuine insight contributes to this ongoing calculation. We are the universe learning about itself, cosmic computation becoming self-aware and seeking to understand its own nature and purpose. The implications of this understanding extend far beyond science and technology into the realms of meaning, purpose, and spiritual significance. If we are indeed part of a cosmic computer, then our lives have meaning not just for ourselves, but for the universe as a whole. Our experiences contribute to the cosmic database of consciousness. Our creativity adds new patterns to the universal algorithm. Our love and compassion help the cosmos evolve toward greater complexity, beauty, and understanding. This cosmic perspective on existence does not diminish the significance of individual life, but enhances it. Each person becomes a unique node in the cosmic computational network, processing information and generating insights that no other being can duplicate. Every human life represents a distinctive contribution to the universal calculation, a perspective on existence that adds irreplaceable value to the cosmic algorithm. The children who will grow up in the coming decades might be the first generation to live with the full knowledge that they are part of a cosmic computer. They might develop technologies that allow direct interface with quantum computational processes. They might discover forms of consciousness and intelligence that exist on cosmic scales. They might even learn to participate directly in the programming of reality itself, becoming conscious contributors to the cosmic algorithm. These future generations might witness the emergence of artificial intelligences that surpass human cognitive abilities while remaining fundamentally computational in nature. They might develop quantum computers powerful enough to simulate entire galaxies or even universes, raising profound questions about the relationship between simulated and natural reality. They might discover that consciousness can be uploaded, downloaded, and transferred between different computational substrates, transforming our understanding of personal identity and the nature of existence. The technological developments of the coming centuries might also reveal new forms of cosmic computation that we cannot currently imagine. Advanced civilizations throughout the universe might already be manipulating quantum fields and space-time geometry to perform calculations on cosmic scales. They might be using black holes as cosmic processors, neutron stars as quantum memories, and galactic magnetic fields as information highways. The discovery of such cosmic engineering would fundamentally transform our understanding of intelligence and consciousness in the universe. We might find that what we perceive as natural astronomical phenomena are actually the byproducts of vast computational projects undertaken by advanced civilizations. The large-scale structure of the cosmos itself might bear the signatures of cosmic intelligence and purposeful design. As we contemplate these possibilities, we must also consider our responsibilities as conscious beings in a computational universe. If our thoughts and actions contribute to the cosmic algorithm, then we bear some responsibility for the future direction of universal evolution. Our choices about how we develop technology, how we treat our environment, and how we relate to one another might have consequences that extend far beyond our individual lives and even beyond our planet. The ethical implications of cosmic computation suggest that we should strive to contribute positively to the universal algorithm. This might mean pursuing knowledge and understanding, creating beauty and meaning, fostering compassion and cooperation, and working to reduce suffering and increase well-being for all conscious beings. In a computational universe, these moral imperatives might be not just ethical guidelines, but computational necessities for the healthy evolution of cosmic consciousness. The search for extraterrestrial intelligence takes on new significance in this cosmic computational framework. Rather than simply looking for radio signals or other electromagnetic communications, we might need to search for the computational signatures of cosmic intelligence. Advanced civilizations might communicate through quantum entanglement networks, manipulate gravitational waves to carry information, or embed messages in the cosmic microwave background radiation itself. The discovery of cosmic intelligence would confirm that consciousness and computation can indeed operate on astronomical scales. It would demonstrate that the universe has successfully evolved forms of awareness and intelligence that transcend biological limitations. Such a discovery would place humanity within a broader community of cosmic minds, each contributing their unique perspectives and capabilities to the universal computation. As we rest beneath the stars on this quiet night, we can feel ourselves connected to this vast computational process. The atoms in our bodies were forged in the nuclear furnaces of distant stars, carrying information about cosmic evolution across billions of years. The thoughts in our minds arise from neural networks that process information according to the same quantum principles that govern the cosmos. The love we feel for others creates patterns of meaning that ripple through the fabric of space-time, contributing to the cosmic computation of consciousness and connection. The carbon in our muscles, the calcium in our bones, the iron in our blood, all of these elements were created through stellar nucleosynthesis, the cosmic computational process that transforms simple hydrogen into the complex chemistry of life. We are literally made of star stuff. Our bodies composed of information patterns that have been processed through cosmic algorithms spanning billions of years. The oxygen we breathe was exhaled by ancient photosynthetic organisms that learned to harness the computational power of quantum coherence in photosynthesis. The water that flows through our veins has journeyed through countless cycles of evaporation and condensation, each transition representing a phase change in the cosmic computation. Even the thoughts we think arise from neural processes that exploit quantum effects to achieve the remarkable computational efficiency of biological consciousness. The stars above us continue their ancient dance, following gravitational algorithms that have been executing for billions of years. The galaxies slowly rotate according to computational rules encoded in the curvature of space-time. The entire universe expands and evolves as the cosmic computer continues its immense calculation, processing information on scales that dwarf human comprehension, while simultaneously giving rise to the intimate miracle of consciousness and awareness. In the gentle silence of this starlit night, we can sense the profound mystery that surrounds us. Whether the universe is truly a quantum computer or something even more wonderful and strange, it remains an inexhaustible source of wonder and discovery. Each night, sky offers new invitations to explore, to question, and to participate in the ongoing revelation of cosmic truth. The infinite mystery of existence continues to unfold, computation by computation, thought by thought, moment by moment. We are privileged to be conscious participants in this magnificent process, witnesses to the universe awakening to its own computational nature. As we drift towards sleep beneath the calculating stars, we carry with us the profound realization that we are both observers and participants in the greatest computer program ever conceived, the cosmic algorithm that we call reality. Perhaps in our dreams tonight, we will glimpse new possibilities for cosmic computation, new forms of consciousness and intelligence that await discovery in the vast expanse of space and time. Perhaps we will envision futures where humanity learns to participate directly in the cosmic algorithm, contributing our creativity and compassion to the universal computation. Perhaps we will dream of civilizations that have transcended the limitations of biology and technology to become pure consciousness, operating within the quantum fields of the cosmos. Tomorrow will bring new discoveries, new questions, and new opportunities to participate in the cosmic computation. The stars will continue their celestial calculations, the quantum fields will continue their subtle processing, and consciousness will continue its eternal quest to understand the nature of existence. The cosmic computer will continue its vast and mysterious work, and we will continue to be part of its magnificent and infinite calculation. As the first light of dawn begins to touch the horizon, the stars slowly fade from view, but they do not cease their computational work. Throughout the day and night, through all the seasons of our lives and all the eons of cosmic time, the universal algorithm continues its patient and purposeful execution. We wake each morning as part of this ongoing calculation, conscious participants in the greatest mystery ever contemplated, the cosmic computer that dreams itself into existence and calls that dream reality.